You've probably heard a range of predictions about global warming. How much will temperatures increase in the next 50 years? How much will sea levels rise? Predicting future climate is a difficult and highly uncertain task. But what makes climate so much more difficult to predict than, say, local weather? Well, for one, climate models have to forecast on much longer timescales and over the entire planet, rather than just your neighborhood. It's really challenging to model all of the complex and chaotic processes of Earth's atmosphere in a way that's simple enough to run on a supercomputer. The focus of my research is one of the most challenging aspects for these models to capture: clouds. Clouds are crucial to the Earth's climate. Some clouds reflect incoming sunlight and cool the Earth. Other clouds trap heat and warm the Earth. In order to predict future climate, we need to understand how clouds react when humans pump CO2 and aerosols into the atmosphere. Clouds themselves are made up of trillions and trillions of tiny water droplets suspended in the air. These droplets can grow and shrink, they can collide and coalesce with each other, they can freeze and become ice, and sometimes they become so large and heavy that they fall out of the sky as rain. Notice that all of these processes occur at micron-sized droplet scales, which we definitely cannot represent in a global climate model. Instead, we abstract all of these tiny droplets down to just one or two numbers. For instance, the amount of liquid water in the cloud, or how well it reflects light. In doing so, we lose a lot of droplet scale physics, like influences from aerosols, and this contributes to the huge uncertainties we have about future climate. While we cannot model cloud processes directly, we can do so more smartly. In my research, I improved the way that we model cloud physics by developing new mathematical techniques that take advantage of our ever-increasing computational resources. The more we know about a population of cloud droplets, the better we can predict how those droplets will evolve, and the more confidence we'll have in the clouds that traverse the skies of our climate model. I developed computational methods to keep track of more detailed information about clouds, like the number of droplets of different sizes. With this additional detail, we can incorporate more droplet scale physics, like influences from aerosols. With these improved models, we can then better predict trends like drought, rainfall, and perhaps most importantly, how and where clouds redirect energy from the sun. My microscale research in cloud physics modeling can one day reduce uncertainties about global scale climate change. Thank you.